In this video, we're going to be talking about limit laws. In previous sections, we relied pretty heavily on calculators and the graphs of functions to be able to find limits. In this section, we will use limit properties called the limit laws to calculate limits. Suppose that c is a constant and the limits for f of x and g of x exist as x approaches a. Then the following hold true. The first limit law says that the limit as x approaches a of c is equal to c. And remember here, c represents a constant function. So let's just visualize what that would be like. So here's my y-axis, here's my x-axis, and I have some constant function that would look something like this. It would be a horizontal line. And so if I were on the x-axis approaching an a value, if I were using the balloon analogy, that would mean that there are two people getting closer and closer to A from both sides, and the balloon wouldn't be changing height. And so this height would remain c, and so it makes sense that this limit would equal c. For limit law 2, it says that the limit as x approaches a of the function x is equal to a, and here's another visualization of that. So notice that the balloons are closing in on this ordered pair right here, and because this is the function y equals x, if I plugged in a, my output value would also be a, and so that's why this limit is equal to a. Limit law 3 basically says if you're taking the limit of a constant times a function, you have the ability to pull this constant outside of your limit and multiply it to the limit of just f of x by itself. 4 and 5 basically say if you have the limit of a sum or a difference of two functions, you can separate that into two different limits and then either add or subtract them. Similarly with multiplication and division, except for division, you just have to make sure that the limit as x approaches a of g of x is not equal to 0. So I went ahead and I wrote that in, and then the last one just says that if you're taking the limit as x approaches a of a function that's being exponentiated, you can take that exponent and bring it on the outside and calculate the limit first and then exponentiate last. Let's look at an example. Example 1 says calculate the limit as x approaches 1 of the square root of x squared plus 5x all over 3 minus x. So using the limit laws, first off what I did was I rewrote the limit as being raised to the 1/2 power because square root and 1/2 power are the same thing. And the reason that I did that was so that I could use limit law number 8. So I'm just going to put an 8 to indicate that that's the limit law that we're using. So now I can rewrite this as the limit as x approaches 1 of x squared plus 5x over 3 minus x. And now this whole thing is being raised to the 1/2 power, or I'm taking the square root of that. From here, I can use limit law 7 to split up my limit into the numerator and into the denominator. Okay, so I've split up my limits. I put a limit in the numerator and in the denominator, and now I'm going to be able to use limit laws number 4 and 5 to split up into even more limits. So what is that going to look like? Well, in the numerator, I'm going to use limit law 4 since that is a sum, and in the denominator, I'm going to use limit law 5 since that is a difference. All right, so at this stage, we have 4 different limits that we need to calculate. So let's rewrite this again using the limit laws. In the top left corner, I have the limit as x approaches 1 of x squared. I'm going to use limit law 8 on the top left corner. On the top right corner, notice that I have that constant 5, which I can take out using limit law 3. And then the bottom left corner, I can use limit law number 1 because I'm taking the limit of a constant function. And then in the bottom right corner, I can use limit law number 2 because we're taking the limit of the function y equals x. So let's go ahead and rewrite this using the limit laws that I just referenced. Also, I forgot to write the 1/2 power here, so make sure not to forget that. Okay, so we were able to evaluate the bottom two limits. And so now we just need to help simplify the numerator, and note that the numerator, we're going to use limit law 2 twice, once for this limit and once for this limit. So let's go ahead and rewrite that. Okay, so at this stage we've evaluated all of our limits, and to simplify our final answer, we're basically just doing some arithmetic. So the numerator will simplify to 6, and the denominator has simplified to 2, and so our final answer is going to be the square root of 3. So down in this purple box here, we have something called the direct substitution property, which says if f is a polynomial or rational function and a is in the domain of f, the limit as x approaches a of f of x is equal to f of a. And something that I kind of want to highlight is this is talking about polynomial and rational functions, but it turns out that in a later section we're going to learn about continuous functions, and this property, this direct substitution property, is not just limited to polynomials and rational functions. In fact, we can do this direct substitution property for other types of functions as well, but we haven't learned about continuity or continuous functions yet, so we'll just leave it at that. Example 2 says find the limit as x approaches 3 of the rational function x minus 3 all over x squared minus x minus 6. Now, because this is a rational function, we could try to use the direct substitution property. However, if we plugged in 3 into the denominator, we would get division by 0. So unfortunately, direct substitution is not going to work here. But what we can do is we can factor the denominator into x minus 3 times x plus 2. And then what happens is the x minus 3 and the x minus 3 in the numerator and denominator, we can cancel those out. And even though the functions are not the same because their domains are not the same, we can still evaluate the limit as x approaches 3 of the remaining 1 over x plus 2. And notice that 1 over x plus 2, this thing, is a rational function. And so we could try using the direct substitution property again, which will work here. And if you're in my class and you're one of my students, I require that my students, when you're first learning about limits, to write capital D and capital S over your equal sign to illustrate that you're using direct substitution at this point. And when we do direct substitution, you no longer need the limit symbol after the equal sign. So because we're no longer taking a limit and we're applying the direct substitution property, I'm plugging in 3 for x, which I can here, and my final answer simplifies to 1 over 5. Example 3 says find the limit as h approaches 0 of the function 2 plus h quantity to the 4th power minus 16 all over h. Now, if we tried to use direct substitution here, we would again get division by 0, so we have to turn to other methods. And the first thing that I'm going to do is I'm going to expand 2 plus h to the 4th power, and you could do that with so many different ways. You could use the FOIL method, you could use the box method, you could even use Pascal's triangle, which I have other videos on all of those methods. So if you're not familiar with multiplying out a power of a binomial, go ahead and watch one of those videos. I'm just going to go ahead and expand that, and it will expand into 16 plus 32h plus 24h squared plus 8h cubed plus h to the 4th power minus 16 all over h. Now, what did expanding that power of that binomial do for us? What we can do now is 16 minus 16. Those are like terms, and they will cancel out. And so now I have the limit as h approaches 0. Notice that every remaining term in my numerator has an h in it, so I can factor out an h outside of the numerator. And if I do that, I will be left with 32 plus 24h plus 8h squared plus h cubed all over h. And again, this is helpful because now I can divide these h's out, and this is equal to the limit as h approaches 0 of 32 plus 4h, 24h, plus 8h squared plus h cubed. Now, this thing is a polynomial at this stage. This is a polynomial, so it turns out that at this point, we can use direct substitution. So I'm going to write capital D, capital S over my equal sign. I no longer need the limit symbol because I'm no longer taking a limit, and I'm invoking this direct substitution property. So I have 32 plus 24 times 0 plus 8 times 0 squared plus 0 cubed. And if we simplify that, that becomes 32. So that's the value of this limit. In example 4 here, we want to find these limits, and notice that direct substitution is not going to work for either of these. So in part A, we're going to use a technique where we are rationalizing the numerator. And so I want to take my numerator and my denominator, and I want to multiply it by a fancy form of 1. And so I'm going to multiply both the numerator and denominator by the square root of x squared plus 9 plus 5. And in the numerator, the way that I can simplify this is I'm going to use the box method to multiply these. So I have the square root of x squared plus 9 minus 5, and the square root of x squared plus 9 plus 5, or just positive 5. And I want to multiply these. In my top left box, I'm going to have x squared plus 9. In my bottom left one, I'm going to have negative 5 times the square root of x squared plus 9. And then in my last box, negative 5 times 5 is negative 25. Now, the whole reason that we're doing this is that you'll notice these are like terms, and they will cancel each other out. So we have x squared plus 9 minus 25. This becomes x squared minus 16. And that is a difference of squares. And so my original limit, we have the equals the limit as x approaches negative 4. My numerator simplifies to x squared minus 16. I'm going to factor that into x minus 4 times x plus 4. And I recommend that we don't distribute the denominator. So I'm just going to write this as the square root of x squared plus 9 plus 5 without multiplying out my denominator. And the reason that is because now we can see these x plus 4s will cancel out. And so we have the limit as x approaches negative 4 of x minus 4 over the square root of x squared plus 9 plus 5, and we no longer have the issue with direct substitution, and so I can use direct substitution at this point. If I do that, I no longer need the limit symbol, so I have negative 4 minus 4 in the numerator, and in my denominator I have negative 4 quantity squared plus 9, and then make sure your plus 5 is outside of the square root. My numerator is going to simplify to negative 8. The square root portion, we have 16 plus 9, which is 25. The square root of 25 is 5. So we get negative 8 over 10. And if we reduce that, that becomes negative 4/5. And so this is our final answer for part A. All right, for part B, we have the limit as p approaches 2 of this rational function. I'm going to factor out the numerator. Notice that I cannot use direct substitution. That would give us division by 0. So I can factor the numerator into p minus 2 times p plus 1. And p minus 2 squared is just the same thing as p minus 2 times p minus 2. Now notice that I can cancel out these linear factors here, so this is going to equal the limit as p approaches 2 of p plus 1 over p minus 2. Now, unfortunately, we still cannot use direct substitution, which a lot of times when we're calculating the limit of a rational function, after we've done these factoring techniques and canceled out common linear factors in the numerator and the denominator, a lot of times we can use direct substitution, but that's not the case here, because if I did use direct substitution, I would still have division by 0. So we're going to have to rely on other methods. But one thing that I kind of know is that here's my y-axis, here's my x-axis. So let's just convert our variables to y and x. So suppose the function that I'm looking at is y equals x plus 1 over x minus 2. I know that there is going to be a vertical asymptote at x equals 2. So let's say this is 2. There's a vertical asymptote here. And I want to observe what is happening as we are approaching 2 from the right-hand side. Well, think about plugging in numbers like 2.1 or 2.01 and stuff like that. So what's going to happen is the numerator is going to be a positive number, and then the denominator is, if I plugged in something like 2.001, it's going to be some really small positive number, and because the denominator is really, really small, the overall fraction is large, and so the values are going to go off to infinity, and so it's going to look something like that. Also note that both the numerator and the denominator are linear polynomials, and so if we thought about the horizontal asymptote, we could take the ratio of the leading coefficients, which is 1. So that means that there is a horizontal asymptote at y equals 1. So my graph would look something like this. And then if I took the limit as p approached 2 from the left-hand side, that would mean that I'd plug in a number like 1.9, and my numerator would still be positive, but 1.9 minus 2 would give me a negative number, and something similar would happen except it'd be negative, and so my function's graph is going to look something like that. And so we can see that this limit, I'm going to erase this limit is equal to positive infinity, and this limit is equal to negative infinity. So because these are approaching different things, the one-sided limits are not equal to each other, which means that the overall limit does not exist. So this is our final answer for part B. The limit does not exist. In example 5a, let's take the one-sided limits. So I have the limit as x approaches -4 from the right-hand side. And again, notice that I cannot use direct substitution because I would get division by 0. And we always want to try direct substitution as a first step, but that's not going to work here. So I'm going to approach -4 from the right-hand side, which would mean that I would be plugging in numbers like -3.9, -3.99, and the numerator is always going to be positive. So if I plugged in something like -3.9, my numerator would be 0.1, and then my denominator would also be 0.1, and so this is going to equal 1. And that will happen for any value that I plug in as long as it's to the right of -4 on the number line. So this limit is equal to 1. Let's see what happens as we plug in numbers that are to the left of -4 of our function. This would be something like if we plugged in -4.1, the numerator is still going to be positive, and so -4.1 plus 4 is -0.1, but we'd be taking the absolute value of that, so that'd be 0.1. And then my denominator, if I plugged in -4.1, that's going to be -0.1, and that's going to look very similar for any x value that we plug in that's to the left of -4 on the number line, and we're going to get an output value of -1. And so let's just quickly graph what this looks like. Here is x equals -4. Everywhere to the right, my output value is +1, and then everywhere to the left, it's -1, and the function's not defined at x equals -4, but notice that here's my person with the balloon. As I approach from the right-hand side, it's approaching here, it has a y value of 1, and then as my person is approaching from the left-hand side, they're approaching this point here, which has -1. So because the one-sided limits are not equal to each other, so these are not equal, the overall limit does not exist. In example 5b, we want to take the limit as x approaches -1 of x squared minus 1 over the absolute value of x minus 1. Now, something that we're going to need to remember here is that back in pre-calculus, you learned that the absolute value function is a piecewise function, and it's equal to x if x is greater than or equal to 0, and it's equal to -x if x is less than 0. Why do we utilize that information here? Well, here we see that the x value is approaching -1, and so we can actually replace the absolute value of x here using this piecewise function, because really we only care about x values that are negative since we're approaching -1. So I can rewrite this as the limit as x approaches -1 of x squared minus 1. I'm going to factor that. That's a difference of squares. I'll factor that into x plus 1 times x minus 1. And then the absolute value of x I'm going to replace with -x. And now what we can do is in the denominator, I can factor out a -1. If I do that, I'm left with x plus 1. And then this x plus 1 here, and this x minus 1, I can divide these out, and this becomes the limit as x approaches -1 of x minus 1 over -1. At this stage, I can use direct substitution. So if I plug in -1 for x, that gives me -2 over -1, and my final answer is +2. And that concludes example 5. In example 6, we want to calculate the limit as t approaches 0 of h of t, where h of t is this piecewise function here, and it has a name called the Heaviside function. So I'm just going to graph what this looks like. Here is my t-axis, here is my h of t-axis. When t is positive or 0, my output value is equal to 1. So here's 1, and it looks something like that. And maybe I'll change colors. So this is the y value 1. And then if t is negative, then my output value is 0. So it looks something like that. Notice that if we use the balloon analogy, if I approach 0 from the right-hand side, that limit would equal 1. And then if I approach 0 from the left-hand side, that would approach 0. So since the one-sided limits are not equal to each other, the limit as t approaches 0 of h of t does not exist. Let's move on to example 7. We want to evaluate the limit, if it exists, the limit as x approaches 7 of this fractional function here. So the technique we want to use is we want to find a common denominator. So I have 1 over x minus 1 over 7 all over x minus 7. I'm going to multiply this by 7 over 7 and multiply this by x over x. If I do that, that becomes, let's see, 7 over 7x minus x over 7x all over x minus 7. Then I can combine that into a single fraction, so I'd have 7 minus x over 7x over x minus 7, and if I wanted to, I could rewrite that as x minus 7 over 1. This is now a complex fraction, and I can multiply by the reciprocal, so I'm going to come over to the side here. I have 7 minus x over 7x times 1 over x minus 7, and I'm going to also factor out a negative from this. If I do that, if I factor out negative 1, then that will give me x minus 7, so I can now cancel these. I'm going to clean this up a little bit. So after dividing out the x minus 7 in the numerator and the denominator, we have the limit as x approaches 7 of negative 1 over 7x. At this stage, I can finally use direct substitution. I no longer need the limit symbol, and I have negative 1 over 7 times 7. And if I simplify that, my final answer for my limit is negative 1 over 49. In example 8, we again cannot use direct substitution because that would lead to division by 0. So I'm going to utilize a strategy that we've used before where we factor the numerator and the denominator. My denominator is a difference of squares, so I can factor that into t plus 1 times t minus 1. Now, the numerator is a difference of cubes, and I have a terrible memory, so if you're like me and you can't remember the difference of cubes formula, one thing that's helpful is t cubed minus 1 is a cubic polynomial, and a root of this is the number 1, because if I plugged in 1 cubed minus 1 equals 0. So I'm going to rely on using synthetic division because I know that 1 is a 0 or root of this polynomial. I'm going to use synthetic division. So t cubed minus 1, if I take its coefficients, they are 1, 0, 0, and negative 1. I add vertically, 1 plus nothing is 1. Then I multiply diagonally, 1 times 1 is 1. I add vertically, multiply diagonally, add vertically, multiply diagonally, and the last number represents my remainder. These are my coefficients, so this is the constant term, this is the linear term, and this is the coefficient of the quadratic term. So we have t minus 1 times t squared plus t plus 1. All right, so now, like we've seen before, these common or shared linear factors in the numerator and the denominator will cancel each other out. And so now at this stage, I should be able to use direct substitution because we've canceled out the t minus 1. Also, pro tip, I highly recommend in math that you write your t's with a tail, because if you don't, it often gets confused with a plus sign. So that's just my pro tip for you. Here we're using direct substitution. We have 1 squared plus 1 plus 1 over 1 plus 1. And my numerator, 1 plus 1 plus 1. That's going to give me 3, and my denominator is 2, so we have a final answer of 3/2. So that concludes example 8 for us. Here we have a theorem that says if f of x is less than or equal to g of x, where x is near a, except possibly at a, then the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x, provided that these limits exist. So what is that saying? Well, let's say at a function, here we have x equals a, so I'm just going to say that maybe it looks something like that. Here, this would be g of x, and then I have some other function this is f of x, and maybe both f of x and g of x do not have a in their domain. So what this is saying is if the function's values near x equals a, so kind of between here and here, notice that all of the function values for g of x are greater than the function values for f of x. Well, it kind of makes sense then that the limit would have to be greater than or equal to for g of x, since g of x is the larger function than f of x. So that's all that theorem is saying. Now, this theorem, the next one, it has a name, so it's probably pretty important. It's called the Squeeze Theorem. And it says if f of x is less than or equal to g of x, which is less than or equal to h of x, where x is near a, except possibly at a, and the limit as x approaches a of f of x is equal to L, which is also equal to the limit as x approaches a of h of x, then the conclusion is that the limit as x approaches a of g of x also must equal L. So here's a really nice picture of what's happening. What this is saying is that h and f are two functions that bound or squeeze or sandwich the g of x function. So g is in the middle of these two functions. So if h of x and f of x have a limit value of L for some specific x value a, then g of x must also share that same limit value. Why do we care about this theorem? Well, it actually helps us out a lot in solving certain limits. Let's look at an example. Example 9 wants us to find the limit as x approaches 0 from the right-hand side of the function square root of x times e to the power of sine of pi over x. Now, I can't use direct substitution here because if I plugged in 0 in here, I would have division by 0, so we have to rely on other methods, and we're going to end up using the squeeze theorem. So we want to bound this function between two other functions that we are able to take the limit of. So let's start off by saying this. I know that sine of theta, where theta can be any angle, I know that because of the range of sine, this has to be between -1 and +1. Now, because theta can be any angle, I can replace theta with pi over x. So we can still say that -1 is less than or equal to sine of pi over x, which is less than or equal to 1. Now, I want to introduce the Euler's number. Because e to the power of x is an increasing function, what do I mean by that? Well, here's my y-axis, here's my x-axis. If I sketched a graph of y equals e to the x power, it's an increasing function, meaning that if I had my x value of -1 here and my x value of +1 here, then here this would be e to the -1. And here on my y-axis, this would be e to the +1. We can see that e to the -1 is less than or equal to e to the +1. So continuing on in my inequality, I can raise all of these or have them have a base of e, and our inequality would still hold true. So I have that, and now the last step is I need to introduce the square root of x. And because we're approaching 0 from the right-hand side, we have that the square root of x must be a positive number. So if I multiply it to all parts of my inequality, the inequality symbols do not need to change in any way because I'm not multiplying by a negative number, I'm multiplying by a positive number. So if I introduce and multiply square root of x times e to the -1, that's still going to be less than or equal to the square root of x times e to the power of sine of pi over x, which is less than or equal to the square root of x times e to the +1 power. And notice that the thing in the middle, this thing here, is our original function that we are taking the limit of. And why are we squeezing it in between these two functions? Well, if you go back to the theorem, we need our function g of x to be the middle one, and we need to bound it or squeeze it between two other functions. And so, again, if we're thinking back to the theorem, this would be f of x, this would be g of x, and this would be h of x. So now, hopefully, I can take the limits of the f of x function and the h of x function, and hopefully they give me the same value, because then we would be able to apply the squeeze theorem. All right, so I want to calculate the limit as x approaches 0 from the right-hand side of square root of x times e to the negative 1. Using the limit laws that we learned, e to the negative 1 is a constant, so I can actually factor that outside my limit. So I have e to the negative 1 times the limit as x approaches 0 from the right-hand side of the function square root of x. Now, if you think back to what the graph of the square root of x looks like, it looks something like this. It's an increasing function. So if I'm approaching 0 from the right-hand side, then the balloon is heading towards the origin, meaning that this is equal to e to the negative 1, and our limit evaluates to 0, and this is equal to 0. I went ahead and I calculated something very similar for the limit as x approaches 0 from the right-hand side of the square root of x times e to the positive 1 power. So what we've shown here is that when we take the limit of our f of x function and the limit of our h of x function, which are these things, they both equal the same value, which in this case is 0. So notice that these things are the same. So we've put all of this information together, and now we can say by the squeeze theorem, it's very important to name drop. So by the squeeze theorem, we can conclude that the limit as x approaches 0 from the right-hand side of our original function, the square root of x times e to the power of sine of pi over x, must also equal 0, because we found that this limit, the limit of our bound functions, were also equal to 0. So that's how we can apply the squeeze theorem. In the previous section, we learned that the limit as theta approaches 0 of sine of theta over theta equals 1. Let's use this to see if we can figure out some other limits. Example 10, part A, we have the limit as theta approaches 0 of 7 times sine of theta over 8 times theta. In part A, what I can do is I can rewrite this as the limit as theta approaches 0 of 7 over 8 times sine of theta over theta. And notice that I cannot use direct substitution, but I can use the limit law that allows me to take out 7 over 8 since it's a constant, and multiply that by the limit of, as theta approaches 0, of sine of theta over theta. Notice that this here is the limit that we have here, and it's equal to 1, so I can now just substitute in 1. So this is equal to 7 over 8 times 1, so our final answer for part A is 7 over 8. For part B, we have the limit as x approaches 0 of x over sine of 4x. So there's a couple issues. In order to use this highlighted thing here, the sine has to be in the numerator, and then the denominator has to be just the variable. And the other thing that we want to concern ourselves with is this thing here and this thing here have to be the same thing. But here inside my sine I have 4x, but here I only have x, and so I need those things to match. So I'm going to do a few things to allow this to work out. First off, I'm going to rewrite this as the limit as x approaches 0 of, I'm going to take the reciprocal and then have 1 divided by the reciprocal. So this becomes sine of 4x over x. Now this is a complex fraction, but if I do the keep change flip method, that would return me to the original limit. So it's okay for me to do this. And another thing that I can do is I can multiply this by 4 over 4. I've implemented this strategy before. We're multiplying something by a different form of the number 1 so that we can get things to work out as I wish. So another thing I can do is I can use a limit law to separate the limit of the numerator, which is this, and then the limit of the denominator. And I'm going to go ahead and move this 4 so that I can multiply it with the x. So now I have 4 times sine of 4x over 4x. And this 4 is in the numerator, which is this 4 here. But again, using another limit law, I could bring this outside, and now I have this. And now this is in the form that I want it to be in here, because I have the limit as x approaches 0 of sine of 4x over 4x. Those are the same thing, and my x value is approaching 0. So this whole denominator piece right here evaluates to 1. And so my numerator, the limit as x approaches 0 of 1, that's a constant function, so that'll be 1. And then I have 4 times 1. So my final answer for part B is going to be 1/4. All right, so for part C, I have split up the limit into 2 fractions. And notice that if I multiply sine of 2t over 1 times 1 over sine of 11t, that will return the original function that we were looking at. And I'm also going to, again, implement the strategy where I multiply by a fancy form of 1. In this case, it would be t over t, so that I can move this t into this denominator and move this t into the numerator here. So let's go ahead and rewrite that. From here, I'm going to use another limit law so that I can split this up into 2 different limits. So this is the limit as t approaches 0 of sine of 2t over t times the limit as t approaches 0 of t over sine of 11t. And then I still need to kind of implement that strategy where I need to multiply by a fancy 1. So I'm going to multiply the first fraction by 2 over 2. And then this one I'm going to multiply by 11 over 11. Let's see what happens from here. We get the limit as t approaches 0. This 2 I'm going to factor outside of my limit. So I have 2 times the limit as t approaches 0 of sine of 2t over 2t. And this 2 I'm just putting there so that this will evaluate to 1. And then let's see, I have times. I'm going to again implement the strategy where I need the reciprocal. So I'm going to have the limit as t approaches 0 of, let's see, this 11 in the denominator, I'm going to factor that outside. So that becomes 1 over 11 times the limit as t approaches 0 of 1. I'm going to move this over because it's getting a little messy. So this is going to be 1 over sine of 11t over 11t. And then I can split this into 2 limits in the numerator and in the denominator using one of our limit laws. And let's see, the numerator here, this is going to evaluate to be 1, and then this is of the form where we highlighted initially, so that's also going to equal 1. So our final answer is going to be 2 times 1 times 1 over 11 times 1. So our final answer is 2 over 11. And that concludes this video on limit laws and calculating limits using the limit laws. Thanks for watching.